Thank you. Hello, my name is David Aurelio. I work on the React Native team at the Facebook London engineering office. And today I'm going to talk about React Native's packager, certain things it does, why it does them, and so on. But first, don't know whether you heard about this before. 2 days ago, we open sourced Yarn. It's a package manager that we are working on together with Google, Exponent.js, and Tilde.io. Compatible with NPM and Bower registries, and it has some nice things, like it's very fast. It has optimized network usage. It has an offline mirror of the packages you installed. It has a version log file and will check checksums against packages you are installing. And that log file will also guarantee that you will always get the same file tree, no matter on which machine. So if you haven't checked it out yet, visit the website. Start it on GitHub. I think we're over 11,000 stars by now, which is quite impressive. And today, I'm going to give you a short overview what the packager is, what it does, the specific challenges that we have been facing at Facebook when packaging JavaScript for mobile applications, specifically React Native. The code optimization techniques that we've built into Packager to make it produce more efficient bundles. Our own bundle format, which is called Random Access Bundle, and the things that we're currently working on. So how many here have been using React Native? OK. How many of you have been shipping something to the Play Store or the App Store with it? OK, not that many. I think one of the nicest thing about React Native is that it gives you a very web-like development experience. You can change code. You just go to your simulator or emulator, hit reload, and you will see the changes immediately without having to recompile your application. And Packager is the piece of software that powers just that. It will rebundle your JavaScript on the fly while you're developing and produce production bundles as well. So what is React Native Packager? It's a JavaScript bundler similar to Browserify or Webpack. And it obviously bundles JavaScript files. That means you'll give it an entry file. It will find all the dependencies recursively, transform all the files, and at the end, write out a bundle. It has some specialized additional features, like handling of mobile assets. So if you require an image or a movie from within your application code, we'll put that into the right places of the file tree and just package it up in your mobile application at the end. It has support for this custom bundle format that I'm going to show you. I would say it comes with a different philosophy than a lot of other packaging tools out there. So as part of React Native, it's very important to us that things run out of the box. So you create your application with React Native in it, and if you then invoke React Native run Android or run iOS, it will just work out of the box. It will launch an emulator, launch the packager, and you'll be good to go. There's no need for a configuration file, no need to add any additional packages. It just comes with a lot of stuff included, like we have transforms for ES6 features, for ES7, JSX, obviously, if you're working for React, and Flow. We always bundle a specific set of polyfills, since we, unlike with web development, we know in which environment your code is going to be executed. It's always going to be sorry. It's always going to be JSC. And we know the baseline of features that exist and what we have to polyfill. So we give you a console API, network API, like in the browser, XML HTTP request, and fetch. ES6 and ES7 features. We also have support for async and await keywords. And we have a specific set of module resolution features that you would have to add to other packages first. So these features for module resolution specifically are, so in your package JSON for browser development, you have this browser field, which we support, and we also support an additional level. You can also put a React Native field in your package JSON, and you can override specific files in your modules with that for the use with React Native to make cross-platform development easier. We also support loading modules by extension. So if you have a module file called module.js, you can put another file in the same folder called module.native.js, and the packager will prefer that over the generic version. And you can also use a platform-specific version if you want to override something for just one platform. You don't have to overuse that, by the way, because we also have a nice optimization step that will allow you to put platform-specific code in your modules without actually shipping them to other platforms. And we support our Facebook internal module algorithm, which is called Haste, and it works by putting the ID of your module in the doc block of your file, and will just allow you to find that module wherever it is in your file tree from wherever. So specific challenges we've had at Facebook is we are using a monorepo, and that means there's just a lot of code, a whole lot of code. Advantages to that are that everybody always has the latest version of the code. Nobody has to upgrade manually, and you will find breakages a lot earlier. It makes it more difficult for tooling because tools have to be able to handle thousands of files. We also have a lot of code in applications. So building a bundle for our applications involves transforming thousands of files, and we don't have much third-party code that lives in node modules that would be pre-transformed. So we pretty much have to transform all of them. And that was this here. And Packager also runs as part of an existing build tool chain, which means there's a lot of CPU contention going on, and we still have to be as efficient as we can be when other parts of the build chain are actually using CPU. Specific challenges for Packager in that regard are transforms and minifications. And if you run them on one CPU, like I think most bundlers do at the moment, it will just be too slow. So we have a worker farm in Packager that we use for transforms of single files and minifications of single files to make that better. I mentioned CPU contention. So better than parallelizing work is obviously to do no work at all. So that's why we have an on-disk cache with all the transformations that you ever executed, and that survives restart. So you can do a second build, or just come back in the morning, restart your Packager, and you will still have that cache of pre-transformed modules to make it go faster. And whoops. One specific thing that can happen, mostly on Macs, is you can run out of file descriptors, which is terrible. The usual answer to that in the Node world is gracefulfs, but we have had our difficulties with that because gracefulfs will basically wait until somebody in your process closes the file descriptor and then try to flush the queue of pending file operations, which won't work if other processes own file descriptors. You will just be stuck forever. And we have had problems also on OS X with kernel pipe buffers that you can fill up, and if you don't drain them from elsewhere, Node will actually block on writes to the console. Now that's another problem we have faced. And we also have, this is not specific. I mean, the most important challenge for apps is startup time. That's probably the most important engagement metric. And React Native is particularly challenging for app startup time because we are starting a JavaScript virtual machine, whereas native code it's precompiled, it will just run. Or in case of Android, the VM will already be running. And JavaScript comes, as code. We have to parse all of that on startup. So that was a significant portion of our app startup time. So I'll talk a little bit about how Packager worked at the beginning of the year and show you how we changed it. In the background, you can see the early history of distributed computing at Harvard, 1890. So Packager mechanics, how it used to work. We had a couple of optimizations for the development mode to make it really fast, but it turned out that we had to change that to get more optimized production bundles. So we would start with the entry file that the app defines. We would extract dependencies with irregular expressions, and that comes with its own class of problems. I'll show you some of these. I mean, it's pretty straightforward, right? You just write a regex that starts with import and matches everything up until from, and then a string. But we also use flow heavily, so you really don't want to extract flow-only dependencies because you might pull files into the build that you're actually not using. And you only need the type. But this is a valid import, so it gets trickier. You cannot just get away. You cannot just get away with a negative look-ahead assertion. And this is a type import again. So it's possible to get this right, but it's very hard. So we changed all of that. And this is another gem, right? It's another type import. So we extracted all the dependencies and resolved them. Repeated that process up until we found all the files that are part of a bundle. After that, transformed all of them in parallel on our worker farm, concatenated them into a bundle, and at the end, minify them if we're doing a release build. Can anybody see what might be slow in this process? So one of the problems we might have is that we might transform code that isn't used. That's specifically true if you have code that runs only in development or in production. And the same thing is true for application startup time. So since we're finding all the dependencies so early, this is really fast, doing it with regular expressions on the raw code before you transform anything. But you just end up with a bigger dependency graph than you need to. So in fact, we had a dead code removal step running on production bundles, and that had to do multiple passes over the whole bundle, thousands of modules, as I mentioned, and that could potentially run for minutes. Which some people get annoyed of if they build mobile apps on their computer and they just have to wait for this step. So we changed all of that to look like this. So again, we started loading your entry point, but we immediately run the transforms on it. If we are doing a release build, we're running a certain set of optimizations. that I'm going to show you on the next slides. And only after that, we'll extract your dependencies. And since the Babel transforms already ran, there are no more type imports. There are no more ES6 style imports. It's all going to be required, so that makes it a lot easier. We're also not using a regular expression anymore. We use a Babel visitor to traverse the AST that we have anyways, and can identify require calls safely. Yeah, we resolve the dependencies, repeat until we have all the files, and we end up with a list of transformed modules. Unlike minifying the whole bundle, like we did earlier, we can now run minification in parallel for each file individually, which obviously is faster, especially on a CI system where you might have 24 cores or more. But minification also isn't an ON operation. So the overall speed of minification is just much better, and then only at the end we concatenate all of that into a bundle. So the specific optimization steps we implemented before the minifier even runs are inlining of values that we know to be constant at runtime, but you don't know the values while you're developing. And then after that, we do constant folding, which means we find constant conditionals in your code and just remove the branches of code that we know to be dead. And that can look like this. So we have 3 specific tests in here. We're testing whether we're in development mode. This is our own constant dev. We have platform.os, which is part of React Native, and will give you the name of the platform you're currently running on. And we have a typical npm style marker where you check for process.env.nodenv. And we're actually consuming React from npm, and React is using that everywhere for development code. So it would be nice if we could just strip it out for production. So we can inline all of these values because we know them at bundling time. We know the platform we're building for, and we know whether we're doing a release build. And now we can easily identify the dead code and just remove it from our bundle completely. And if we run dependency extraction after this tab, we're just going to end up with way less code. And we actually leave blocks intact, so you can use block scope variables without messing it up. We try to push this one step further and find dependencies after minifying the code. But I mean, the minifier is probably better than our optimization step that runs on very specific things to strip out that code. But minifiers can transform code in very unexpected ways, and that just makes it way harder. So we tried it. This is an actual transformation that happens, that can happen. So the easiest thing here is to find the name of the require function after minification. It gets way harder to analyze this call because you kind of expect a single string. And sorry. So there are tricks to make this work, but they just add a lot of complexity to the code. And you never have the minifier under control. If somebody just happens to upgrade Uglify because of a too greedy Semver version range, you might actually break somebody without even knowing it. So it's better to run our own optimizations. We have that under control, and it doesn't change the structure of imports in your code. So we can just, we know what we're looking for, and just have a way easier, our job just gets a lot easier. So by having less code in our bundle, we obviously can lessen the parsing stress on the VM at app startup time and get a faster starting app as a result, which is nice. With our methods, we can optimize the typical NPM ecosystem conditionals. We can optimize for release. We can optimize for platform. So this probably gives us like 80% of what we need, and seems to be good enough. But this doesn't solve our fundamental problem, which is that growing applications increase parse time linearly if you build a bundle for them. So if your product engineers add code, add features, it will end up in your bundle, and the bundle will grow, and the JavaScript VM will just parse for longer time. So our biggest startup time improvement didn't come from any of these optimizations, but from our own custom bundle format, which we call random access bundles, which allow to pull in additional modules in constant time. So random access bundles allow us to load code on demand when the application requires it. If you require a module in your code and it is not known to the module system, we call into native code, and we expose a function from C++, which is called native require. We just pass the module ID to native require, and from C++ can load the code for that module and inject it into the VM lazily. So that's the main benefit of this technique, that we actually only have to load what's required for application startup for the startup. And as you use more features in your app, we can pull in the appropriate code for that. So our module factories in React Native look something like this. We have this global D function. You pass it the ID of your module. So you are not doing this. This is the result of our bundling process. And the factory for your module. And this will be important later. And I'll show you why. So the file format for this is relatively straightforward. So the idea is to split your code into a startup section that mainly contains non-module code like polyfills and the initial require calls that kick off your application. We ended up with different file formats for Android and iOS just to get the maximum speed out of it, possibly. The iOS version is just using a binary offset table at the beginning of the file, whereas for Android, we just package individual files in your APK, which is basically a zip file, because that was just the fastest way to access them. So for iOS, the file will start with a magic number. So if you want to use this feature, you don't have to actually change any of your code. We'll just auto-detect it when we're loading the bundle by checking for this magic number. It will have another 30-bit integer, which is the number of modules that we have in that file. We have the length of the startup code, the startup section. And after that, for each module we have two integers, the offset into the file and the length of the module, so that we can read efficiently from the file. And after this offset table, we'll just have your regular code. It starts with the startup code. For Android, this looks very different. So as I mentioned, we have individual files. We have the name of your bundle, bundle.js in this case, which contains the startup code. We have a folder called JS modules with numbered files, and this unbundled file, which is only 4 bytes long and contains our magic number so that we can do runtime checks what kind of bundle you're actually loading in the application. And remember, module factories, I wasn't telling the whole truth. In order to make this work, especially for the offset table, we need numeric module IDs, and they have to be continuous. So this is what code actually looks like, and this will be important for the next steps. So random access bundles. They're useless if you do regular requires or imports, because you will just lazily require all your dependencies at the top of your module. So you're going to end up to pull them eagerly, and it's going to be slower than a regular bundle because we have a certain call overhead between C++ and JavaScript. Not very useful, unless you don't load all of your code eagerly. And this is what we phrase the term inline requires for that. So how does that look like? Simple. So if this is one of your modules, and say this is part of your application navigation, you might have a main screen, you might have a detail screen, and depending on some condition, you show one or the other. To make this work, to actually profit from random access bundles, you would just move that in line and call it lazily. So there's nothing really complicated to it. Doesn't work with ES6 imports, obviously, but I mean, we support both mechanisms, so just use what you need to for the specific case. And we also have a Babel plugin that we're using at Facebook that does this automatically. So your developers will write regular module code with requires or imports at the top, and this transform will move all of them at the point in the file where they are actually used. So you have a little bit of call overhead, but you get the benefits without having to change your code manually. Caveat with this small transform is that it doesn't work very well with ES6 modules, so pull requests probably welcome. And I think somebody also wrote this for ES6. And we did some other custom tricks internally. There's nothing magic to it that you couldn't do. It's just more complex. And if you're interested, just talk to me later. I can explain to you how you can make it work. So we started moving more code into the startup section, because if we know which screen is going to be shown on startup, we know what code we need for that. And we can just use the transitive dependencies of a certain file to mark all of these with a special property and make our bundling process move them into the startup section. So we get rid of the call overhead into C++ on application startup. And we also started moving stuff into groups of modules that belong together for certain parts of the application or for certain libraries. Or as an example, you could just group together all of React, and as soon as you require any module that is part of React, you'll just load all of it all at once. And this works by putting all of these JavaScript modules into one of these numbered scripts. So relatively simple, but can be tricky to set up. And in one of our applications, of our side applications, this application ended up being interactive more than 25% earlier than after the various iterations that we put into this technique than just loading a regular bundle. So if you want to use this yourself, somewhere in your build scripts, in your Gradle files or your Xcode project, there's a call to the React Native CLI tool, and it invokes the bundle command to create a bundle. If you want to profit from random access bundles, just have to change it to this. So finding the location in your build files is probably more tricky than adding these two letters. And yeah, if you want to make your application start up faster, just give it a try. OK. How much time do I have left? Not that much. OK. I'm going to show you what we're currently working on to make the bundling or packaging experience even better, even faster. Because at scale, we're still struggling with the time it takes, and we just want to make ourselves more productive. So we're working on two things at the moment. Currently, we're doing an integration with Buck, which is our build system. And I guess nobody here is using it. It's open source, it's great. But it's still great news, because we're investing a lot of work currently to make the overall architecture better, so everybody will profit. And this will also make the development server better in the end. Give you a very quick introduction to what Bug is. It's a build system. We use it for our mobile applications, but not only. It figures out the target graph of your build and will run builds in parallel as much as it can. And it will, if you have an application as the build target you're building, it will just build all the prerequisites in the right order on all of the CPUs you have, and just finish everything before it invokes dependent rules. It will only use files that you are telling the system to use, which means you get very reproducible builds and faster builds. So you don't end up having different builds maybe on different machines because somebody has a dirty checkout or whatnot. And one of the best features is that it has a distributed cache API that if you're using Bug, you can just set that up for your organization. And if our CI has built something, it will be in that cache. So if you build a mobile app on your machine, you can pull down everything from the cache, and you will only need to rebuild what has actually changed on your machine. And if somebody else built it before, you will get it. So we want to integrate with that as much as possible to save bundling, packaging time for our pipeline. So goals here are faster rebuilds and leverage Bug's cache as good as we possibly can. And currently, Bug only invokes the packager and uses the created bundle for subsequent build steps. And that means we only benefit from the caching at the bundle level. But if your bundle already takes over a minute to build, then you still, for every JavaScript change, you have to rebuild for a minute. Which for some people might be unacceptable. But yeah, that's the way it is right now. And our goal is to cache transform results for every single file in the source tree, because transformation, together with minification, is the computationally heaviest operation Packager is doing. So we want to get rid of that as good as we can. And to achieve that, we have to separate the build into two phases. One is obviously transforming all the files that might go into a build up front, and then have the bundle as a step that's separate from that. And by pushing all the computationally heavy works into the smaller cacheable transformed files, we can have a really fast bundle step, because that will run for every change, obviously. So the problems with that, and I guess I have to speed up a little bit, are that Bug needs to know your JavaScript dependency graph. And if you're a JavaScript developer and already using imports or require, you don't want to duplicate it. You don't want to declare your dependencies in your Bug build files. And but we need some kind of information. The second challenge is that I showed you what the module factory looked like. It had these global IDs of modules, and these IDs are very specific to a certain build because they have to be continuous. So the transformed cache files must not contain any build-specific information. That's the second challenge with that. We're solving the first challenge by forcing users to declare a very rough approximation of the dependency graph. You could, for instance, so Bug files are just Python files. You could declare two libraries, one for your own code, one for your dependencies. And Bug will all the magic in the background to create single file targets. And your bundle would then depend on these libraries. And that way, we try to make it as frictionless as possible. And the second challenge that I mentioned was having transform modules without any build-specific information in them. And as I said, the idea of the module that we're constructing is in there, and the IDs of our dependencies are in there as well. And the way we're solving this is to move the global IDs into an array that we pass to the D function, so we can create require function that is specific to that module and will just do the right thing and just index our require calls internally. And this is important for caching and source maps. We'll just move the bundle ID down there. And what we're doing in the transforming steps is not creating that at all. We'll just end up with a raw factory. So what's great about that is that we can just append all the information we need without messing up source maps, because if you add something up front, obviously, your source maps are going to have offsets, which is just bad for development experience and whatever else you might be doing with source maps with your production apps. So we're creating independent build artifacts for files, and we'll have a fast and safe manipulation of those in the bundling step. And this was also great for the development server, because we can cache files more efficiently. I mean, we're kind of doing this already, but we'll get much better source maps than we currently have, and we'll also make this bundling step faster. We also started rewriting the core. Basically, mainly the module graph. This is the part in the packager that will load a file. It's basically the coordinator, the controller, if you will. It knows to talk to a service that loads files. It knows how to talk to a service that extracts dependencies. And this new implementation supports bundle deltas, which we cannot really do at the moment, which means we can efficiently recalculate what changed between two instances of the same bundle after you change your codes. And we backported this in a very hacky way. This landed like 2 months ago. You should have that in your current version already. And we call it back updatable bundles. And this doesn't show you much, of course. So if you run packager in verbose mode, if you change a file, you will find this somewhere in the output. We attempt to update the existing cached bundle. We transform the file that you changed, which in this case is just our index file. And in this case, it took 247 milliseconds. And this time is when we actually flashed out the request to the simulator. It takes 297 milliseconds, which means that for these in-place updates of bundle, we're now bound to the transform time for the file and no longer to traversals of the dependency graph as we were before. Only works if you don't change any imports. Then we currently have to discard your bundle. But the goal is to make that work also with our new core. So bundle deltas are great because they will kind of unify the logic between refreshing and hot module reloading. It will just be the difference of pushing versus pulling. And it has the potential to move the cached bundle to the device. Now, what does that mean? So currently, your packager server has the cached bundle, and whenever you re-request it from your device, we'll just serve the in-memory version of it that we now can update. But we actually could move the bundle into our C++ implementation, cache it there, and just talk to packager via the WebSocket and get updates streamed to the device. And then will just be a device switch, whether you want hot module reloading or not, can just switch it on or off, and we can do the appropriate things on the device. So that should make the experience a lot snappier than it currently is. But we'll see about that. So that's all I got. You can find me on GitHub and on Twitter, and I also have a Facebook account. Thank you.